Hello. In the previous video, we discussed how the assumption of energy quantization supported from Einstein's explanation of photoelectric effect helped Max Planck solve the infamous ultraviolet catastrophe. Now, this meant that light was both a wave, which was always believed before the ultraviolet catastrophe was solved, and then with Einstein's explanation, it was said that light was a particle as well. Now, in this video, let us see how an experiment in the 1920s in the Bell Laboratories at New Jersey changed the very course of modern physics. It was the discovery of the weird and contradictory wave-particle duality, the wave-particle nature of light, and ended up as an epic battle fought between the greatest minds in science and for the highest possible stakes, the nature of reality itself. Now, before we talk about the experiment and what its results were, let's see what its theoretical backing was. Now, in the 1920s, approximately, it was confirmed that light was an electromagnetic wave. So, scientists came forward and explained the phenomenon of black body radiation, of interference, wave interference, using the assumption that light was a wave. The phenomenon of diffraction, interference. You have phenomenon like diffraction and interference, which was helpful in determining that light was a wave. Interference implied that light was a wave. But then photoelectric effect said that light was a particle. So there was a conundrum there. Now, this was a mystery yet to be solved, and scientists of that period desperately wanted to understand what the nature of light was. Now, in the year 1923, a young French physicist by the name Louis Debrogile came up with an interesting theoretical theory where he proposed a hypothesis to explain the theory of atomic structure. He tried to explain atomic structure. Now, mind you, atomic structure is remarkably different from what light is at that stage in the 1920s. So, atomic structure was remarkably different from the nature of light. Now, by using a series of substitutions, Debrogile hypothesized that particles also hold properties of waves. Now, Debrogile first used Einstein's infamous equation relating matter and energy, where E is equal to mc squared. Now, this is for photons, where their momentum comes out to be 0. So, Einstein said E is equal to mc squared, where energy was equal to mass times speed of light squared. Now, name this as 1. Now, using Planck's theory, which states that every quantum of a wave, we've discussed this before, which says that every quantum of wave has a discrete amount of energy given by Planck's law, which said that E is equal to h mu. Right? Now, this was basically an assumption used by Max Planck to explain the ultraviolet catastrophe, and its predictions were true. And that's how a scientific theory keeps on building. It was a model which explained the observed phenomenon and predicted certain things remarkably well. So Debrogile used Einstein's formula for energy and matter, and then used Planck's theory, which said that energy of a quantum of wave was proportional to its frequency. Now, since Debrogile believed that particles and waves have the same traits, he hypothesized that the two energies must be equal. He believed that particles and waves, this was for waves and matter, and this was basically energy was for waves. He believed that matter and waves have the same traits, and he hypothesized the energy must be same. So a simple equation of 1 is equal to 2 gives us mc squared is equal to h mu. And by using the relation that mu is equal to, now one important assumption is, because real particles do not travel at the speed of light, Debrogile substituted velocity for the speed of light. So that would gave us mv squared is equal to h mu. Now from wave theory, we know that mu, the frequency of a wave, is equal to its velocity by its wavelength. So substituting that on the right hand side of this equation, we have mv squared is equal to hv by lambda. Now I can cancel a v on both sides, vv. This gives us that lambda is equal to h by mv, or h by p. Now p is the classical momentum of a particle. Now this is something remarkable, and we need to stare at this equation for a while. Now what this says is, given a particle whose momentum is p, then we know that it is also a wave and its wavelength is lambda. Or given a wave whose wavelength is lambda, then its particle-like momentum is p from the simple equation. Or this could also mean that the wavelength times its momentum is a universal constant. So for any particle, its wavelength times its momentum is a constant. This wavelength was called the De-Brogile wavelength. Now this was all the theoretical backing for the experiment. Now we talk about the remarkable experiment which shook the entire physics community. This was an experiment conducted in the Bell laboratories in basically between 1923 to 1928. This was called the Davisson Germer experiment. Davisson Germer experiment. Now, I would not go into the exact details of the experiment. I would attach a good source for that in the details below. But this is roughly what it did. Now, we already knew from Thomas Young's experiments in the 1800s that if you have light, a parallel light source being emanated from a point source, and you have two slits here, you have a barricade with two open paths, two open slits, and you have a screen which captures light, you would usually obtain an intervening sequence of bright and dark fringes. Now this is what was called the phenomenon of interference, and that gave us interference fringes. Mind you, this was light, right? Now, if the similar experiment was what Davisson and Germer did was they performed a similar experiment for electrons. Now you had a source, basically nickel metal, which constantly emitted electrons, right? And then you had similar two slits like this. Then you had a screen. Now what we'd hypothesize with electrons as particles was, as electrons are emanated from this point, it just passes through one of the slits and lands here. One of the slits and lands here or lands here, right? But what was remarkably found was that after a large number of electrons were fired, very large number of electrons were fired, the pattern obtained was not something like this. This was the classical pattern should have been predicted, but the pattern obtained was exactly like this. The pattern obtained was an interference fringe like this. So interference fringes for electrons. Now this said that if electrons were emitted from a source via two slits, you get interference, then electrons are waves. But what the whole community had thought till that point was electrons are particles and waves are completely different. Now we even explain photoelectric effect with light as particles, but we assumed that light were waves before. But now we thought electrons were particles, but electrons are out to be waves. So the whole theory, so we arrive at this grand theory that everything has dual nature. Everything is a wave and everything is matter. This was how we confirmed the wave particle duality. Everything was a particle and had an associated wavelength given by the previously derived De-Brogile wavelength. Right? And what was even more remarkable was if you repeated the same experiment with higher precision, mind you, this was conducted many years later. If you had two slits like this and you fired a series of electrons one at a time, now mind you, the very picture of me drawing particles might be misleading. Let me erase that. So you have a source of electrons here. Source of electrons. Now if you keep firing electrons one at a time, then it would pass through one of the two slits and gradually you would get spots here. Right? And spots are quite random, and after a large number of electrons are emanated point by point, point after point, then you get the beautiful interference pattern here. This confirmed the wave nature of electrons, and this was in line with Debrogille's theoretical prediction wave particle duality. Now if you go a little further and try to calculate what the wavelength of this electron was by using this, now this turns out to be 6.63 to 10 power minus 34 joules second. Now the mass of an electron we know today is 9.1, 10 power minus 31 kg, and this into assuming 6 meters per second. Let's assume the velocity of the electron was this, 10 power 6, right? Now if I use my calculator, the value I get is 1.46 into 10 power minus 10 meters. Now this is 1.46 Armstrong. This is the wavelength of an electron with this velocity. This is a wavelength of an electron. Now can you imagine an electron as a wave? Well, welcome to quantum physics.